Okay, let's see. Navigation panes, hide. Pages. Okay, I'm gonna go ahead and share my screen on here. Why is it not showing up? Okay, cool. Cool. Okay, sorry about that, y'all. Should be back now. Yeah, let me just make sure that everything's recording like it should be. Yeah, I'm pretty sure it's getting that. Okay. So, right, so where were we? I was talking about piecewise functions. So, like, a lot of times we can define signals over an entire domain. Like, they'll just have one behavior, like, say, something like sin x. Like, we know that it'll be wavy over the whole real line. But we don't necessarily have to restrict ourselves to defining like waveforms that look like some behavior in one region specifically. And like we might say something like use a case statement, like where it's 1 for where t is less than some value, t, and then it's 0 elsewhere. And then this looks like a box. It's a rectangle function. So when we have a different piecewise behavior, we can typically represent these with we can typically section these different regions of behavior using the step function. So like this rectangle function from 1 in this boundary t to negative t, this can be written equivalently as where it's 1 from some u t minus tau to some like minus some negative u t minus tau. Let's see, I'm not on my computer anymore. Oh yeah. Let me do that. All right, I think that should show up well now. Let me know otherwise. Plus like some u t minus tau. I think that's right. But the idea that I want to just point out here is that we can use the step function to section off different areas of the time axis that we have. So like that's all I wanted to touch on with just what a signal is and how I'm going to be talking about them here. So like some important things that we need to talk about in the course is like we can do different things to these signals. So we can move them left and right. So like if we have some box, we can move it to the right by going like having the same function. So like let's say that this white is f of t. we can move it to the right by going t minus tau, where tau is just some constant, and we can move it correspondingly to the left also by saying that this is just f of t plus tau, where tau is some constant. So we can move it back and forth. Right, so we can also move the values of the function up and down. So if we have like some box, again, I like boxes, so I'm going to be talking in terms of them a lot. They're just easy to draw. So like if we have this rectangle function where it's 1 and then 0 everywhere, we can move it up and down with addition. So like if we wanted to move it up, we'll just go f of t plus some a, some constant a. This is a plus 1, this is a. And we can also move it down similarly. So like we can also do things like stretching and scaling them. We can stretch them horizontally we can stretch them outwards so that they look larger. So like if we have a box again, we can stretch it out by halving it, or multiplying it by some constant that is less than 1. So 1 over a times t. And we can scale it by something, we can scale it smaller also, horizontally, by just doing something similar. We can go f of t, a times t. This constant a is like a factor that scales the signal up and down depending on what the value of it is, right? So we can also scale these things vertically by multiplication. So like if we have a box again, should have maybe drawn these boxes ahead of time, but we can multiply this value by some constant a, and then we'll get the same function, but just scaled vertically. So this is a times f of t. And then we can also cut them off using the step function, like we were talking about a little while ago. We can partition the time axis into different regions by just summing up different step functions. Like we have this one step function that is like u of t minus a, and like this one would be another step function, where this is u of negative t minus some b. Right, so we got that. So that's all great. That's all great. And another thing that we can do is we can sample a specific value of any signal that we have with the delta function. So the delta function is just the signal. It's a distribution technically, but like it's not something that is covered very thoroughly in this course. So the functional definition of the delta function that we'll be working with is where it's 1 for when t is equal to 0, and then this is 0 elsewhere. And notice that like this is just a spike at 0. Like, that's how we'll draw it. And we can move it left and right by doing these same things to the delta function. We can scale it, we can shift it, we can do everything that I just went over with the delta function. And multiplying some signal by this delta function it has a unique property of just giving us wherever that delta function is 1 at. So in this case, this would be f of 0. Like if we multiply just some function by the stock delta function, we can get different values of this function f by just moving around our delta function. So if we went f of t times delta t minus a, for instance, then t minus a is 0 when t is equal to a. So this will equivalently give us f at some constant a. So like these are signals. This is how we manipulate them typically. There's not really too much more to this. And this really just defines how we're going to do a lot of our algebra in terms of signals. So this brings us to just what is a system, like y'all are talking about in class. So in effect, a system is just the functional definition that I like is that if we just have some black box and we put some input into it, like some input signal x of t, we'll get out some signal y of t. And for the most part, this black box can really be anything. Like all we need, like for the purposes of engineering, this system can be any function that we can realistically do on x to get y. So like we'll often talk and like we'll talk about designing different components of like say a circuit or some program in terms of systems, and these blocks, like we'll typically give them names like h of t. So it's just a thing that takes, so a system is a thing that takes one thing and then produces another. And like so like in order to have this thing be useful, this h, then we'll typically design, like we'll need a couple properties from these to like make them useful to work with, because like there's no point in defining a system that is impossible to realize or make or whatever word you want to use. So like yeah, so this system H is going to satisfy certain properties. We're going to want it to be LTI. So yeah, the property of linearity, so like for any constant a and b, so they're constants. So we'll have h of t, h of a plus b, a t plus b. This will just be equivalent to a times h of t plus b. Wait, hold on. Let me check my notes real quick. So there's supposed to be some other constant here, c. Yeah, so it'll be like, let's call it t1 and t2. This will be h of t1 plus b times h of t2. So like if we have a system that's time invariant, we'll have for every constant tau, then we'll have that h of t plus tau is equal to, wait, let me get my notation ready. Okay, so, right, let me start again. So we're going to have a signal x1 of t and some other signal x2 of t. And this system will act on these two signals for all of these properties. So again, like let's take some alpha and beta, some constants, and then a linear system is one that satisfies that h of alpha times x1 plus h times beta x2 is equal to alpha h of x1 of t plus beta h of x2 of t. Right. So like a time invariant system is where if we have some y of some x of t minus some constant tau, and we have the signal given the signal x of t, then for any constant tau, we'll have x of t minus tau will give us a x of t. It'll just be the output of the system where it's x of t minus tau. So if we have a shifted input, so if it's shifted input, then we'll have a shifted output. So and it'll be shifted by the same factor t tau. Right. Let me try and write this more succinctly. So like if we had given some box, then if we know that it produces a triangle when we pass it through H, then if we have a box that's shifted over, then if we apply H to that, then it'll give us a triangle shifted over by the same amount. Yeah, where this is just tau. This one's tau. Right, so a causal system is also another property that we want. What's that? What's that? Yeah. Right. Do you mind sending me the question that you're talking about? Like, because time invariance can be done in different ways. Like it's just a property that you need to prove, like with just the construction that you have x and then you shift it over and then you get some. You need to prove that h of that x shifted is going to be shifted out. Yeah. It's like send me that. Try and get me that problem, and like I'll try and get that towards like the end of the session. So like my idea is that we'll just go through some of the properties, just to kind of give a very brief overview of everything, and then we'll start hitting problems. Yeah, just to. Okay. Yeah. I'll try and. Yeah, just try and DM me problems. Or post them in the review whiteboard, I guess? Yeah, I think that would be good. Right, so a causal system is one that we have. Like, so any value so if we have some function x where it's not dependent on. So a causal system H is one that depends only on past values of x. So if we have some x of t, this is not going to depend on anything less than 0. So we're going to have where the h is h of x of t is equal to this. It's only going to be dependent on what's to the left. Let's see. So what this is going to mean in effect is that if you have the impulse response of our LTI system, this is going to mean that the impulse response doesn't have anything to the right side of this. This is going to be 0. That's not going to be included in the support. It's only going to have a support that's starting from 0 and goes to up to negative infinity. So this one would be causal. Wait, hold on. Mix that up. Yeah, it needs to be only on the right side. So it needs to be from 0 to infinity, because when we do convolution with a signal for the system, it needs to be all the way on the left when we flip it, if that makes sense. So like a system with memory is typically going to be a system that has values outside of 0. So it will involve values of x that are from the past or present. So a signal that, so if we have a system that is represented by its impulse response, h, then we'll have values on the left or right side of the impulse response if it has memory. If it does not have memory, then it'll probably just be some function of the current value. So like, say some h t is equal to x squared of t, or x, or h of t is some x of like the absolute value of t. These are examples of memoryless systems, whereas an example of something with memory will be something that depends on a past or future value. So say something x. H of t is x squared t plus 2. This depends on the value minus 2 on x. And I probably should have put this first, but the LTI systems are special because we can entirely determine like the output of an LTI system just by convolving whatever input we have with like the impulse response that we have. They're completely represented by h of t. And this is really important because like we typically are looking at systems that are very complex. So if we can completely determine the output given an input, it really makes it a lot easier to analyze this, like a system that we're trying to design or build or whatever. So like I'm going to talk a bit about how we measure signals. So if we have a signal that is with a finite support, then it's absolutely integrable. So like we define something called the energy of the signal. So like if we want to denote that with like an E, then like this energy of this signal x is going to be just the integral from negative infinity to infinity of x of t, like the magnitude squared of it. Yeah, the important part is that you're getting, one thing that I always used to forget is this magnitude squared part. And it's just because like we don't want to have negative values contributing. We just want to get just an overall picture of how much area is contained in this signal. So like if we have so like that's great for finite support signals like the box or a triangle or even a sink, because the sink will die out at infinity. So like we have a finite energy to it. But this is less useful for things that are mainly periodic, and more generally they just have an infinite support. So like this one's the energy. So like if we want to take the power of some periodic function, then we're going to take the average of this integral. The time average as we like let the window that we're taking the average over get bigger over in a limit. So like tau approaches to infinity, 1 over tau of this same integral. So negative t over 2, t over 2 minus. And then the same thing inside, the magnitude squared, dAt. So yeah, that's great. That's great. We can measure signals, we can move them around, and we can manipulate them with systems. An LTI system is something that manipulates a signal. And we can determine the output entirely using the impulse response. Right, so like, I want to talk a bit about convolution. So like, in like the space of signals, the convolution of two of them is going to be similar to like multiplication of numbers. So like, just what this means is that there's going to be a lot of properties of convolution that are going to be very similar to that as multiplication of real numbers, for instance. So if we have like some function, so like we'll have the delta function. It acts as the identity of this operation. So what that means is that if we have any x of t and we convolve it with a delta function, then we'll get the exact same thing out. So like if delta t was a system, then we'll have x of t just taken right back out, like of this delta. So like this convolution operation is going to also follow something called the associative property. So like it doesn't matter what order that we convolve two signals. So like we can move around parentheses, x of t convolved with y of t, convolved with z of t. So like they're commutative, so you can switch around terms that you are convolving. So x of t convolved with y of t is just the same thing as y of t convolved with x of t. And like we can also distribute these convolutions. So like x of t convolved with say y of t plus z of t is the same thing as convolving first x and y, and then also adding the convolution of x of t convoluted with z. Right, so like there's some math facts, and it might be non-obvious how these things will help us solve problems, but I'm going to show you a cool trick that I figured out the other day that will simplify a lot of the convolutions that you'll see on your exam that use a lot of these. So like, they're good to know. Right, so a few things that I like would be pretty beneficial for you to remember for your exam would be that so we can convolve things with a shifted delta, so like delta t minus a. So like this would be a spike that's somewhere else. And then if we convolve it with some signal x of t, this will be the same thing as going x of t minus a. because like we're just moving over the x of t. It's like it's a scanner almost. It's the delta function like scans it in place. So it would be moved over to wherever that delta was. Right, and like another identity that's kind of useful for solving problems is knowing that two rectangle functions, so like this box that I've been talking about, so this box convolved with another box, so the unit box is from -1 1/2 to 1/2, and this one's the same. And remember that this has area of 1. And then this will give us a triangle, which is going to be from -1 to 1. And remember that the maximum area of these two is 1. So if we multiply these two at their maximum, there would be 1. So this is going to be 1 at its max. And like so something that's going to be useful for solving problems, especially if you're in Fumigali's class, is like the geometric series. He particularly likes these types of problems. So if we have some AR from N, where R is some number that is less than 1, then it could be like a fraction or something. So then this function, so the summation of this geometric series, like as we go to infinity, is going to have a number at, oh, that's not supposed to be infinity, that's supposed to be 1. And that's just going to be a over 1 minus r. And like we also know the value of the geometric series when we take the sum from to a finite number. So if we say big N up to big N, sum from 1 to n is ARN. And that's just going to be 1 minus r to the n over 1 minus r. A. Right. So those are helpful for solving problems. Another useful one is the summation from k, like just of the index variable itself. So I probably should have used k's up there, but that's okay. So if we had the summation from 1 to infinity of just the index variable k, then this is going to be k times k plus 1 over 2. And like one other one that might also come up, I don't think that they'll bring it up in your exam, is 1 for k squared. So this will be k times k plus 1 times 2k plus 1 over 6. Yeah. And like just remember that the summation of 1 n times is like n. That's also something that comes up commonly. These are particularly useful. What's that? Oh, y'all have covered Fourier series? Oh, okay. Right. Yeah, it's like I'll cover Fourier series and Fourier transforms in the next review, but like, yeah. So like, yeah, so these will arise if like we have some signal, like a discrete time signal. So if we have a x of t, so x of n, let's say is going to be 1 over 4n, which is going to be just 1/4 to the nth power, because 1 to the n is 1. So like, this is going to look, and then I'm also going to multiply it by ut, just so that it's 0 starting like, I'm going to make it a left. left step function. So like it's going to be like going downward as it approaches. Oh wait, no, hold on. What am I talking about? It's just going to be a regular step function u of t, and then it's going to go down. So 1/4, 1/16, 1/4 to the third, 1/4 to the fourth, and like this kind of signal might use these series to take the energy. So like energy of x of n is going to be this. It's going to use this series, and like yeah. So also one that might be useful, like these summations of variables, like for of the index, they might come up if you just had like some x of n, like let's say like x of n is equal to just n, and where it just goes up infinitely. 1, 2, 3. So like, I imagine if you took like a convolution with this, it would come out to it would involve a series of this nature. So like, they're good to remember for the problems that you're going to be presented in this course. Yeah. Also, a trick that I discovered a little while ago that I'm not sure is taught very often is like this theorem from this guy called Titchmarsh, where basically he says that if you have some x of t and which has a finite support, like from which ranges from a to b, say, and then some other, let's make that triangle, some other function y of t, which also has a finite support, so from c to d, then the convolution of these two signals, xt times xt convolved y of t, is going to have bounds that range from a plus c to b plus d. And in effect, this helps us like determine the bounds very easily using the two signals that we have, as long as they have finite support. And a lot of times when I'm working these types of problems, it allows me to just kind of avoid doing a lot of the work that make convolution annoying. But in the case that you can't use this theorem, then we're going to have to actually know how to do convolution here. So like, I have a bit of a foolproof method for getting the convolution of two signals. So like, let's see, I'm gonna make this bigger. Right, so like, let's say we had some x of t, which has some behavior. Let's say we had an input signal x of t, which is a piecewise function, which has behaviors like, say, like 1, 3, 5, 0. So for at just some boundaries, like so like t is ranging from like 0 to 1. Like t is ranging from, say, 1 to 2. This one's 2 to 3. And then this one's elsewhere. So like, it's going to be just like this step that's going up. Right, this is our x. So and let's say we're convolving it with some function h of t, which is just going to be a regular box, because I'm lazy. T belonging to -1/2 to 1/2. And is 0 else. So we have h, which is just a box. So what we can do is use these properties of these different properties that I just went over of convolution, that in order to break this problem down into something that's very manageable for us to compute. So like what we're going to do first is we're going to break down x into its different piecewise behaviors. So I'm going to say that x of t is, it's going to be, isn't this x of t the same thing as going that we have some box from 0 to 1, it added to some box that's from 0 to 2, add it to some box that's from 0 to 3. Oh wait, that shouldn't be a 0, that should be a 1. And this is from 2 to 3. Right, because we can just separate all of these different boxes that we have in here. So like, we have these 3 x's. And then what we can do is use the distributive property of convolution in order to convolve it with our h, which is just going to be one box. Right. So like yeah, so what you want to do first is to choose the signal that you want to like flip and shift. You'll typically want to choose the signal that's easiest or whatever. You'll want to just try not to use the one that's has an infinite support, like say like the step function or like some exponential that's decaying. You wouldn't want to use that as the signal that you flip and shift, like just because it's kind of hard to define boundaries on those, like for this method. So so I'm going to choose h of t that we're going to flip and shift to. I'm going to put that in red. So like step 1 is red. So one thing that you'll want to do is you'll want to rename the function that you have, h in this case, like in terms of t. So what that means is that you'll have, so if we have h of t being this box from 1/2 to 1/2, so like what we'll want to do is rename this, all of the important points here, so important being negative 1/2 and 1/2, basically the boundaries where the behavior changes. We'll want to rename it in terms of t. So we're going to set the 0 point to be, we're going to call it t, and then we just need to space out these important points similarly as their distance away from 0. So this is how far away from 0? This is 1/2, so it'd be t plus 1/2. And this one is to the left of 0 by 1/2 units, so it would correspond to the name t minus 1/2. Right? It's going to look the same, but this is important when we start deriving bounds, to rename everything, because we're going to put these back in once we have all of our different our poses, that I'm going to call them, and then we're going to use these names to derive boundaries. So right, so what does that mean, poses? So the cool thing about breaking all of these behaviors up into single components like this is that we can use the distributive property of convolution in order to compute all of these. So like the y of t here, which is going to be, let's see, I'm going to move things down. Yeah, it's the right place to move things down. Right. So like we can use the distributive property. So like y of t, which is x of t involved with h of t. It's going to be equivalent to h of t involved with x1 of t. This one's x1 plus x2 of t plus x3 of t. x2 of t and then x3 of t. Right, so we can distribute this h across. So like this would be x1 of t convolved with h of t plus x2 convolved with h plus x3 convolved with h. And these are all functions of time. So like, in effect, what this means is that we can just convolve box by box and then we'll get our answer. So like, yeah, we have, so at this point we've renamed our flip and shift function h, and then we're going to draw the poses. So for a finite support signal, we're going to have 5 different configurations on where the two signals are going to be with respect to each other. So like that's going to be when h is, so let's pretend all of these are some box that we're keeping static. And then, so we're going to have, if we're flipping and shifting our h, then we're going to be, so there's 5 different configurations that we can have. We can have where it's all the way to the left, where it's not overlapping a little. It is not overlapping at all. And then it's overlapping just a little bit on the left. It's overlapping completely on the, it's overlapping as much as it can in the middle, and then it's going to overlap slightly on the right, and then it's going to overlap not at all on the right again. We're going to get 0 for those 2 where they're not touching, because convolution is just going to be the area. Right, I probably should have written down the formula for convolution, which the definition of it. So like x of t involved with h is equal to the integral from negative infinity to infinity of x of t times h of t minus tau d tau. Yeah, and what this definition says is that we flip and shift and take the area as we go. Yeah, so we're going to want to be figuring out the behaviors of the area. So at this point, we've got our poses. So I'm going to copy all of these. Oh no. Let's try that again. Okay, cool. So we got poses, copy, paste. And we're going to write in the names of all of these. So this is where the renaming part comes in. Because if we, I'm going to try zooming in a little. Yeah, so if we had, what were our names again? So t minus 2, t plus 2, and t. So this one is from, so let's just label these t plus 2, t plus 1/2, t minus 1/2, t plus 1/2, oh wait, it's minus 1/2, t plus 1/2. And like this signal is going to be sure to write in the bounds for this signal that we're keeping static. So like I'm just going to take one of these, say x1. So let's call this 0 and 1. 0 and 1. So this one's also going to be from 0 to 1. And like this one will also be from 0 to 1. And this one will also be from 0 to 1. This one's also 0 to 1. And this one's t plus 1/2. T minus 1/2. T plus 1/2. T. Hey, does someone have a question? Is everything all right? Okay, let's see. Yeah, so I'm just labeling everything again. T plus 1/2. Alright, so we have all of the bounds, and now we just need to start writing inequalities, basically. So like, when will it be that this t minus 1/2 and t plus 1/2 is less? So let's just write down what we have in our situation right here. So like t minus 1/2 is less than 0, and t plus 1/2 is less than 0. So like we know that this is just means that for when t is less than 1/2. So like if we solve out these inequalities for t less than 1/2, t is less than minus 1/2. And then this is just the same thing as writing that this is t is less than 1/2, negative 1/2. Because like that's the stricter condition here. So when t is less than 1/2, we'll have this one case in our signal. So let me just try and write out this whole big convolution here. It's just, I'm going to just mark as we go. So the bounds from t is less than negative 1/2. It's going to be some behavior x1 of t. And like, wait, we're calling our output y. It's y1 of t. And then we'll do this similarly here. So we'll have t minus 1/2 is less than 1. So we notice that these should be overlapping. Let me redraw this. T minus 1/2. Yeah, so this t plus 1/2 is less than 1, but it's greater than 0. So t plus 1/2 is less than 1 and greater than 0. So what we need to do is just solve for t again. So for when t is less than 1/2 and it's greater than negative 1/2. Great, so that's our two. I'm ignoring the left side of this just because like it's still all the way to the left. It's not going to create a stricter condition than this right one. So like we'll have some y2 of t that's t from t minus t/2 t minus 1/2. And like, so we'll do the same thing for here. So we notice that we want t plus 1, t minus 1, 1/2 is less than 0. Wait, let me redraw this again. I redefined things, sorry. So we have unit box. We have our signal which is unit box. So like this is t less than 1/2 is less than 1, and t plus 1/2 is greater than 0. But wait, it turns out that it should come out to giving that, so when t is equal to 1/2, it should be this behavior. So we have t is equal to 1/2. So like in general, this is going to be some inequality, but just because the widths of these are the same, it's just a value. And like we'll have, yeah, when it's slightly overlapping on the right, we'll have t, so t minus 1/2 is greater than 0, but t plus 1/2 is greater than 1, because this is to the right of 1 and this one's to the right of 0, and it's less than 1. So like solving out for t again, we'll have from t is greater than 1/2, 1 and 1/2, and greater than 1/2. So let's keep track of that here. y2t. Let's write that down. And this will be y4t. T is less than 3/2, less than 1/2. And like if we have this last one, notice that nothing's overlapping. It's similar to the first case that we had, where everything is overlapping. And yeah, just to be formal, we know that when t is less than 1/2, t minus 1/2 is greater than 1, because t minus 1/2 is greater than 1. So this will be when t is greater than 3/2. So this is y5t. So t is greater than 3/2. Right, so after you do all those steps, basically, you can determine the bounds. That's kind of a long way of determining bounds here. The way that I like to do it is using that theorem that we went over a second ago. So basically, if we have this 0, 1, and we have our -1 to 1/2, then like we'll know that there's some behaviors from -1 to, so like we know that there's some behavior from -1/2 to, because it's -1/2 plus 0, where 0 is the left side of this one and -1/2 is the left side of the other one. And then it's going to be the right side of this, so 1 plus 1/2, so 3/2. And then there's some behavior in here. But anyway, that's one way we could have approached this also. So yeah, so we got all these bounds. Now the hard part is over. That's typically the worst part of doing these. And then from there, it's just doing the integrals. It's really just a matter of having so we know the behaviors of these two, since we broke everything up into single behavior functions. And then we're going to have one behavior times another behavior within the bounds that we just described. So like we would have like an integral of 1 times 1 like 1 times 1, 1 times 1, 1 times 1 from the bounds that we just defined, basically. So like this starts at 0 and then ends at t plus 1/2. We need to take the bounds of the overlap. So like just to do those real quick, I'm going to show you that y2 t is equal to the integral from 0 to t plus 1/2 of 1 dt. And that's just t plus 1/2. And like y1, y4 is similar. So it would be from y is t minus 1/2 to 1. Let me redraw this again. Right, just to get my scale correct again. Yeah, so, and this is just going to be the integral from, yeah, 1/2 to minus 1/2, because it starts over here, just slightly overlapping. And then it's going to be t minus 1/2 to 1 of 1 dt again. And that's just going to be t plus 1. So that's going to be 1 minus t minus 1/2. So that's going to equal to 1/2 minus t. So yeah, notice that we're going to have some kind of ramp. And like the way that you check that these things are right are just basically looking at the two signals and seeing, like, if we were to get the two signals right on top of each other, then what would the maximum area be if you were to multiply these two? Like, that should be your max value. So like, yeah, notice that like the area of each of these is 1, so the max area will be 1. So we're going to get a max value of 1 here at this y3. So like, just to write this down, yeah, so it's 7:16 right now. So I'll just write this down real quick. So this would be t plus 1/2. T less than 1/2. 1/2. And then this would be 1/2 minus t plus t times 1/2. And then it'll just be 0 else. Right. So like yeah, I guess that's one example of how you do convolution. Now, what you do after this is get the convolution of all three of these. So you just do a similar process, but like with all three of these functions, and then sum them up in the manner described, and then you should be able to get the output. So I guess it's time for questions. Does anyone want me to cover anything like specific here before like I go on and just do more examples? Right. What's up? Right. So we know that I probably chose the not the best example here, but it's just like so these bounds that I had were the same size. So this 0, 1, its length is 1, and like this box that I was convolving with from negative 1/2 to 1/2, this is also of length 1. So like, we know that the convolution of these two signals at their peak value will just be like all of the area enclosed in both of these. And since they're the same size, it's just going to be some value. It's not going to vary at all. Like Like, if we had a signal that was longer, like say -1 to 1, then we'd get some trapezoidal behavior in here, this y3 of t. And this would be from some bounds, like 1/2 to -1/2 or something like that, depending on the lengths of these two signals. It's like all of these are relative to their lengths. Like basically, that's the only parameter that really matters, and the rest of them are just shifted and scaled versions of the rest. So like y1, y3, and y5, we know that y1, since it's all the way to the left, this is our, it would just be the multiplication of like two signals that don't overlap at all. So there's no area to take, and we would get a 0 value correspondingly, and we'll also get, yeah, it's just, it's just like, I always thought it was more thorough. Yeah, yeah. Yeah, let's see. So I could go ahead and do some more examples. One that I wanted to get was one where like it's infinite and finite support, because like this method, like I should probably show you all how I would do these fast. So like basically, if I were to just define the same function, so x of t, and then we have our function x of t. So I'm going to do like the same thing that I had before. So like this 5, 3, 1. Right, so this one is going to be, so this convolved with this 1 convolved with plus, so this is -1/2, 1/2, 0 to 1, -1/2, 1/2. So this is plus this convolution of this 3 that's shifted over, convolved with 3, 3, plus convolution with this box again, convolved with the 5 that's also shifted over. So like, I know that these are from 1, 2, and 3. And this is from, so this is 2 to 3. This is 1/2, -1/2. This is 2, 2, 2, 1, 1/2, -1/2. Right, so I have all of these, and then I just take the left side plus the left side here, so -1/2, to 1/2 plus -1/2, 1/2 plus 1, the right sides, add them, so that's 3 over 2. So that's going to be these two values, so it's just 1. Right, so that's our bounds. I know that, so this is where that identity that two rectangles evolved with each other is going to be a triangle from the bounds from 0 to 1, -1/2 to 1/2. So we know that the area of this one is 1. We know that the area of this one is also 1. So this is going to be a triangle that's peak is 1, 1/2, and then it's going to be 1, and then yeah, and this is going to peak at, I think, 1/2. Yeah, 1/2. And then this one will be similar. We're going to, we can take out the 3 here, so this would be like -1. This box convolved with 3 times a unit box from 1/2 to 1 to 2. And so this would just be, again, a triangle. So 3 times a triangle of that's starting at 1 and 1/2. So 1 and 1/2. So 3 halves. 3 halves. And the left side plus the left side there, so that's 1/2. So it starts at 1/2, and then it ends at 2 plus 1/2. That's 5 halves. So we'll have a triangle there, and then we'll have another triangle here. Similar, we'll do this trick of taking out this 5 here, and then we'll just add this similarly. So we have a box that starts at 2. This starts at 5 halves. Great. So this is centered at 5 halves. So we would just have a peak at 5 halves. And then the left, so 2, so it would be 3 halves. Left side plus left side is 3 halves, and then right side plus right side is 7 halves. And then we'd have our 3 signals, and then we'll just add them together. So yeah, it'll be, this is t plus 1/2. So this is 1 minus 1/2. So this is 3 halves minus t plus 3 halves minus t. Let's see. So 3 halves up 1. This is a slope of 1, so it'll be 5 halves minus t plus 7 halves minus t. So like this will be all one behavior. Wait, no, hold on. Usually I have to draw these on top of each other in order to make sense of it. So like, let's see. So -1/2 to 1/2 to 3 halves. And then this starts at 1/2. And then this one starts at this one all the way to the right starts at 3 halves. So this will be like some t. So this is, we notice our bounds here. Like, so you're going to have different behavior from 1/2 to 3 halves, then 5 halves to 3 halves, and then 7 halves to 3 halves, or 5 halves to 7 halves. Right. So as basically, it's just like a matter of getting the equations of all of these lines, then adding them together within these boundaries. So this line is, I'll use a different color here. It's green. So this is 3 halves minus t, and then this one is 3 halves. So this one's minus 1/2 plus t. And then this one is going to be like 5 halves minus t. And this one's going to be 1/2 plus t. So this is going to be like -3 halves plus t. And like this is going to be 7 halves minus t. and like that's the only one that's there. I should have drawn this like that. Really not used to using a tablet. I don't know if you could tell. Yeah, so like you just add these up, and then you have our final answer. So this will be, oh wait, I should probably say that this is 1/2 plus t here. Right, so like our final answer would be like, so from t is bounded from maybe 1/2 to 1/2. So like, notice that all of these, like when you sum these two functions in these boundaries, they're going to sum up to a constant. Notably, so like I'm just going to say, so 3/2 minus t plus negative 1/2 plus t. Notice that this is equal to, so minus t, those will cancel. And then minus 1/2 plus 3/2 is going to equal 1. And if we do this for all of these, this one too, you'll see something similar. So yeah, 5/2 minus 3/2 is 1. Plus t minus t cancels out, so you're left with 1 when you add these. So yeah, our final answer is going to be negative 1/2 to, for t is less than, greater than 1/2, negative 1/2 to 1/2. It's going to be 1/2 plus t. It's going to be 1 from t is 1/2 to 5/2 t. And then it's going to be this final function, so 7/2 minus t. Right, so like, yeah, from 5/2 t minus 7/2. Right, so like, yeah, that's our final answer. It'll look something like a trapezoid. Oh wait, hold on. I forgot to add the constants though. So like, this would actually be like 3 times this one. So like, shoot, I should have done this earlier. Can't see things. So like, since we took out a 3 here, this would be 3 times that. Since we took out a 3, this would be 3 times that. This one would be, since we took out a 5 here in our convolution, we're going to have to get 5 times that. And then this one will be 5 times that. So like, what's that? What's that? What's that? Here? The top? Yeah. Yeah, so this right here? Yeah, so it's basically like, because of linearity, that one property, we can take out constants from our convolutions. Yeah, because our signals are linear, we can take out a constant. So alpha x, which is 3 times our x there, we can take out that alpha. So we can go alpha plus, like, alpha times whatever our convolution is, times x. So does that make sense? Great. Yeah, so I think that, like, this is a good example of why the properties of convolution are important to remember, just because, like, you can break up your problem from something complex into something that's manageable, especially within a time limit. So like, yeah, Yeah, so we have about 30 minutes left. I'm gonna do. I'm thinking about one more example of convolution, unless anyone else has any other like questions they want to touch on. It's like really hard to read a room when it's like I can't see y'all. I don't know, dude. It's like, yeah. Yeah. The review should be posted on the IEEE YouTube page after I'm done here. Yeah, it's like, let me just check that everything's been recording, and it has. So, yeah. So you'll be able to look at this later. I think I've included a lot of the items that are going to be tested. I'm not sure if I've touched on examples for everything though. So like, let's see. Because it's like when I took signals, the majority of the first test is just convolution. Maybe simplifying systems down, but I feel that convolution does test a lot of these properties if you look at the problems in the right way. So like I guess I have one more question on convolution, I guess. So like I'm going to take some signal x of t, which is, so I'm going to be doing a convolution of what's called like a truncated exponential. So this is just the decaying exponential negative, say, 2t, cut off at 0. So this is multiplied by a step function. So this is going to be our input. And like, so I'm going to convolve it with a decaying, like with a ramp function. So like, this is going to be h of t is, so it's 0 elsewhere, and it's from 1 to 1. So it's 1 minus t, or t is less than 1, greater than 0. Right. So like I'm gonna do this problem. Does anyone else want to suggest anything that's like specifically covered, like was mentioned by the professor Buso or Fumagalli? Right. So like one question that I foresee is like they might ask you to take some convolution, and then they'll ask you to take the energy of it. So yeah, I could do a problem where we compute energy. Yeah, so like, yeah. So let's go ahead and try and, what's that? Not exactly. What I meant by that is that what I think might be on the exam is maybe like a several part question where it's like they'll ask you to take an energy, or they'll ask you to compute it for some signal, and then you'll get like, you'll have to convolve that signal with something. Maybe I'm just speculating here. I don't actually know what's on your exam, but like yeah, yeah. It's just kind of like yeah. So let's try and take this energy real quick of this truncated exponential. So like I've been denoting it e of x. This isn't a universal notation, but this is the one I decided on for some reason. So like this would be the integral of x of t from negative infinity to infinity dt, the magnitude squared of it. That's ugly. Write that better. X of t. Magnitude squared dt. Right. So what we know about the signal. So I'm going to go ahead and plug this into the integral here. So x of t is e to the negative 2t u of t dt and then we're going to take the magnitude, square it. So taking the magnitude and squaring it here, I'm going to, so since this is just since everything here is positive, the magnitude of it is just going to be the same thing, negative 2t, ut. Wow, it seems like my writing's rotating. So we square everything. So like the step function squared is just the same thing as the step function. So we can ignore that. And we can say this is the integral from negative 2t squared. And then we know that taking the power of some power is just multiplication, so that's negative 4t ut dt. Just trying to be very thorough here. Negative infinity to infinity e to the negative 4t ut dt. And then, yeah, so when we're integrating a step function, we know that this cuts off boundaries. That's basically the only reason why we use the step function. It's basically to just chop signals wherever we please. It's just so that we can represent we can write a signal in just one line without doing this curly bracket stuff. So when we integrate over a step function, the integral will then just be taken from the boundaries of the step function. So since it starts at 0, like the step function goes from 1 to 0, we integrate over the support, the starting at 0, and then we go all the way over. So this will be from 0 to infinity, e to the negative 4t dt. Yeah, and this operation gets rid of the step function. So what we're left with is this integral negative 4t over 4 from 0 to infinity, and then this will be, so it'll go to 1 over negative 1/4. Or like, if you just take this limit as it goes to infinity, it'll go to 0, and then if we subtract this minus 4, oh, so it'll be plus 4. Yeah, that's it. So that's our energy. Yeah. Any questions? Yeah, so like power, it's going to be less important for signals that are aperiodic, just because like power is necessary when we have infinite support. It would go to 0 in the limit, just because like we'll be dividing by an infinity if we were to take the power. Like the average power of this would be 0. So the average energy, I guess. Just because like there's all of this 0 over here, and if we just take the average of a bunch of zeros, it'll go to 0 eventually. So that's how we'll get. So I guess it's called, like, this is an energy signal. This is an energy signal. And something that doesn't go to infinity, something that doesn't have an infinite support will typically be an energy signal. If you have like the only kind of exception to this is like where, so in order to be an energy signal, it just needs to go to 0 when you approach infinity in either direction. So like that's basically the criteria you need, like, for it to be an energy signal. So like if I were to do a truncated exponential that's like the absolute value of this t, it'll look something like this. like where it's just mirrored on the y-axis, over the y-axis, it won't go to like under their drawing. Yeah. So like it'll be something like that. Yeah, where it's mirrored across the y-axis. So this would also be an energy signal. So because like as we look at the signal as it goes to infinity, it goes to 0. If we look at this as it goes to negative infinity, it would also go to 0. So like yeah, so it really depends on the style of the question. Like I don't think that's I can't say for certain on what the question's going to be, but I would be able to compute the energy of any aperiodic signal that you have, and then I would be able to compute the power of any periodic signal that you have. So like basically, and then know that if you take the power of any energy signal, it'll probably go to 0. Just because like we'll be dividing out by an infinity, like as we take this limit as t approaches infinity. Yeah, so like as t approaches infinity, we'll be dividing some integral, which is just some number, from 0 to negative. Oh yeah, we'll be dividing it by infinity, and like usually that'll go to 0. Sometimes it doesn't, but I think that might be out of scope. Yeah, so I guess I'll do one example where we do power. Yeah, so I'm going to take, say, some periodic function. Like, I'm going to take, like, just like a pulse wave. Yeah, so like this will be so where it's 1 for all of these positive values, and it's -1 for all of these negative values. For everything, so like let's say that this has a period of 1 and a duty cycle of 1/2. So like it turns from 0 to 1 and 1 to 0 every 3 halves, 5 halves. Oh wait, that's 2, this is 5 halves. Yeah, it goes up on 1, goes up on 2, goes down on half, goes down on half. Right, so like the power of this x of t, so let's call this x. So this will just be the integral as we take t to infinity of this average value of -1. T 2 to t over 2. T. So like when we take the power of a signal that is periodic, this average value will be the same if we take any subset of this periodic function. And what this means is that we don't have to take this t as it approaches infinity. For periodic signals, so like let's say, so we know that this is periodic with value 1. Like notice that x plus t is the same thing as x plus t if you shift it over 1, or to the left or right, as a period of 1. Yeah, big T is equal to 1. Yeah, these are taus. Yeah, so like this becomes equivalent to just taking the average value over a single period. So if we just want to take the power over this whole signal, we'll take the the average energy over this one period. So we choose one, and then we just compute the integral, and then we divide by the period. So like p of x of t is equal to 1 over big T times 1 to 1/2 to 1/2 of 1 to -1 x of t. So like I'm going to choose the period centered at 0. So this would be 1/2, and then it would go to, so it goes down at 1/2, it goes up at 0, and then it's still down at 1/2. Yeah, so like it'll just be the integral from x of t dt. So like this will just be period 1. So big T is 1. So it'll be, so I'm going to go ahead and split this up just because our signal is like going to look something like it's 1 for t is, absolute value of t is less than 1/2, less than like 1, and then going to be -1 for t, 2k plus t. It kind of escapes me. Yeah, so like, yeah, we'll basically just break it up into the integral of -1, -1/2, 0 dt plus 1/2 to 1 dt. That's because like the way I drew it is where it's -1 on the left side and it's positive on the right side of the x-axis. Ooh. So like, yeah, this would just -1 times 1/2. Yeah, so like this integral will be like -1 times like the integral from 0 to -1/2. We know that if we flip the, if we do 1/2, it'll be so like 1/2. I'll just go ahead and do it negative. So 0 minus -1/2. So it'll be positive 1/2. And then we'll get -1/2 again. And then 1/2 minus 0. And then this will come out to 0. So like this power is equivalent to just saying the average value. So like the DC level of the signal. So like for periodic signals, we can typically just draw a line through where all of these positive and negative values come out. So like we can just take the midpoint of all of that, and then that'll probably be our power, just because like it'll be like the power of this one will be 0 because like it has a 0 DC level. It's centered at 0 on the y-axis. Does anyone have any questions? Am I contradicting anything? Yeah. Pretty much, yeah. That's the way that I'm seeing it, yeah. Oh, wait. Shoot, hold on. So, anyone catch my mistake? It's like the problem here is that you need to take the squared magnitude. So like this solution is not right. Let's see, it's not 0. If we take the squared magnitude, it'll actually just be 1 across. So the integral over that is over any subset is 1 is 1. So like basically, I don't know if y'all have gathered from this review session, I find it easiest to work with pictures of these signals. So like if you can get some idea about how like these signals look geometrically, a lot of times we're just taking like the area of a simple function, or I'm pretty sure this will come out to 1, the power, just because like we took the squared magnitude. So like if we take the magnitude of -1, that'll just go to 1. And if we square 1, it'll go to 1. So all of these negative parts will be 1. Yeah, the power is taking the average value of a non-negative function. So like I'm pretty sure that you'll only get a 0 power when you have like a 0 signal. So like it's just 0 all the way across. Okay, I'm much more satisfied with this explanation than my previous one. Let anyone know. Let's see, when did I start this discussion? Like 5 minutes ago, 10 minutes ago, 45, 10 minutes ago. Yeah, so I'll probably leave this as a note in the chat. Yeah, later. So yeah, anyone else have any comments, questions? Yeah, man, it's no problem. It's like I don't know. I'm very dependent on trying to get people's reactions when I say things, and it's like it's hard to get that when like I'm staring at a screen. Yeah, I'm hoping that these things will go better in other sessions that y'all attend. Yeah. It's like, this is a hard course, so good luck on your exam. I do think that these things, what's that? Yeah, it's like, it's very much a, I don't know, technical difficulties. I don't know what happened. Too many things went wrong today. Yeah. All right. Yeah. Thank y'all. Thank y'all. Yeah. Good luck, guys. I'll be around for a little bit if anyone wants to ask any more questions. Yeah. Yeah, it's like pretty much you can just DM me at any point. Like just try and at me on the tutoring page, and I tend to get with it. I'll tend to check every hour or so. So yeah, if you want to get to me faster, I'm on Twitter a lot. Just follow me at jluckenba2, like Luckenba, my last name and my username, and like I might respond to you there. Yeah, you can just contact me any way you can, and I'll try and get back to you. Yeah, yeah, yeah. What's that? Yeah, it should be posted that I'm supposed to be tutoring from like 3 to 5 on like a Tuesday, something like that. Forgot what time I actually put. I really actually just check the chat whenever. Yeah. Yeah, usually we'll meet on Discord and we'll just talk through a problem. Like, I tend to be a bit better about answering specific questions. Like, it kind of varies with me on these off the cuff lectures. Like, yeah. Yeah, man. Yeah, man. I'll look forward to it. Great. Yeah. Yeah, yeah, everything's going to be posted on the IEEE website. Yeah, that's no problem.